Welcome to our virtual lab tour for today's explainer. Think of me as your friendly professor for the day, right? Because we're going to embark on a pretty awesome scientific journey. We are decoding a revolutionary testing technology that honestly we've all heard of, but very few of us actually understand. Yep, we're talking about PCR. We're going to walk step by step through the actual stages of molecular testing and uncover exactly how this specialized lab equipment gives us such incredibly accurate health results. So let's dive right in. Picture this. You've got a tiny, basically invisible drop of evidence. Let's say a microscopic drop of blood from a crime scene. It is literally so small that traditional testing methods wouldn't even stand a chance. So how do scientists actually extract usable information from, well, almost nothing? Today, I'm going to show you exactly how molecular biology solves this massive problem and, in the process, completely transformed modern medicine. Okay, here is our lab directory for today's explainer. We'll be hitting up 1, the DNA photocopy machine, 2, inside the thermal cycler, 3, RT-PCR for RNA viruses, 4, counting with digital PCR, 5, accuracy through nested PCR, and finally, number 6, a quick PCR lab summary. Let's get moving. All right, station 1, the DNA photocopy machine. The foundation of PCR is, essentially, it's a biological photocopying machine. Look, if a doctor or a crime scene investigator only has a microscopic trace of DNA to work with, they simply wouldn't have enough material to study. It's just way too small. But by taking that single trace and multiplying it into millions or even billions of copies in just a few short hours, researchers suddenly have a highly visible sample. And this speed, it's an absolute game changer. Faster testing means doctors get results quicker, which means patients get the exact right treatment without those agonizing delays. Moving down the hall to Station 2, inside the thermal cycler.
Now, let's track a patient sample right through the actual testing stages. First up is denaturation. Here, intense heat is applied, and that basically causes the two strands of the DNA double helix to just split apart and separate. Next, in the annealing stage, the machine cools down a bit. This lets these specific trackers, called primers, physically latch onto the exact target area we want to copy. Finally, in extension, the temperature goes back up slightly, and the new DNA chains are actually constructed. This whole cycle, it repeats about 30 to 40 times, literally turning one single strand into billions.
And you have to meet our microscopic builder here. Normal enzymes, well, they'd be totally destroyed by the intense heat of that first denaturation step. But Taq polymerase, it is a highly specialized, heat-resistant enzyme. It actually survives those extreme temperatures, so it can meticulously build our billions of copied strands using raw nucleotides. It's basically the tireless construction worker of our molecular laboratory. All right, let's keep going. Station 3, RT-PCR for RNA viruses. Now, there is an absolutely critical difference between standard DNA samples and common threats like the flu, COVID-19, or HIV. You see, these viruses don't carry DNA at all. They carry RNA. And because our machines kind of can't copy RNA directly, we have to perform this brilliant little reverse translation trick. We use a specific enzyme to convert that viral RNA into readable DNA first. Only after this prep work is done can the standard photocopy process even begin. And that is exactly how doctors precisely identify which virus is making you sick. Up next, Station 4, counting with digital PCR. While standard PCR tells us if a virus is there, digital PCR gives us absolute quantification. It's amazing. Imagine taking a single test tube sample and splitting it into thousands of microscopic water droplets. The reaction then happens individually inside every single droplet, which allows the machine to physically count the exact number of positive hits. No more guessing. Doctors get an exact count. This droplet method is a literal lifesaver when it comes to detecting tiny cancer mutations, and having those exact numbers helps doctors figure out the highly specific medicine dosages required for really complex treatments. Let's check out Station 5, accuracy through nested PCR. Standard PCR usually runs just one round of copying, right? But that sometimes risks a non-specific binding error, like latching onto the wrong piece of DNA. Nested PCR completely fixes this by running a 2-round zoom-in approach. The first round copies a larger area. Then, the second round uses these nested primers to zoom in on a much smaller, ultra-precise target right inside that first area. By basically double-checking its own work, nested PCR bypasses any initial mistakes, giving us super accurate identification. And honestly, that level of precision is what gives patients true peace of mind when they're waiting on health results. All right, almost done. Station 6, PCR lab summary. Let's quickly summarize our toolset here. Standard PCR acts as your basic multiplier for DNA. RT-PCR is our go-to for converting and identifying RNA viruses. Digital PCR offers absolute precision and quantification for rare mutations. And nested PCR acts as the ultimate failsafe for complex or error-prone samples. When we understand these different precision levels, it shows us exactly how doctors choose the right test to decide on the absolute most effective treatment for a patient.
Okay, before we wrap up today's explainer, let's do a quick pop quiz. Think back. Which technique acts like a DNA photocopy machine? What heat-resistant enzyme builds the new strands? Which method requires converting RNA to DNA first? Which variant uses thousands of water droplets for exact counting? And finally, which test uses 2 rounds of primers to fix binding errors? Take a second to see how many you can get right based on the stations we just explored.
Is a pretty fascinating thought to leave you with, isn't it? When we look at how PCR has evolved, from simple multipliers all the way to systems that can physically count individual microscopic droplets of DNA, we realize we're entering this era of truly unprecedented medical clarity. It really goes to show that the closer and more accurately we can look at the building blocks of life, the more precisely we can protect our future. Thanks for hanging out with me on this Explainer Lab tour.